Thank you all for being here. I'm Gloria Palmer, the Executive Director of Green Mountain Academy for Lifelong Learning. Today's presenter is John Delano, and I'm truly delighted to have you with us today. John, prior to retiring in 2016, he held the rank of Distinguished Teaching Professor at SUNY Albany in the Department of Atmospheric and Environmental Sciences. He was an associate dean for the College of Arts and Sciences, having 22 academic departments and 500 faculty, and he was the associate director of a NASA Astrobiology Institute at Rensselaer Polytech Institute. He was a member of many science advisory panels for both NASA and the National Science Foundation. His research was competitively funded by NASA for more than 30 years and yielded 70 publications in the professional science journals. He has given a number of talks for us in the past, both in person and on Zoom. And one of our most popular talks was the stone walls of Vermont and New York State. And so we're just delighted to have you back with us again. Thank you, John.
Thank you very much, Gloria. It's always great to be back here at GMALL. Well, welcome everybody. This is, I hope, going to be a really fun evening as we talk about the first interstellar object that has been detected going through our solar system. This came from another place in our galaxy, and I'll be describing two outstanding hypotheses about its origin. And I hope you enjoy the trip. First of all, of course, as we probably all appreciate, the universe is ancient and unfathomably large. And keep in mind that this Oumuamua, the scout from interstellar space, is from another part of our galaxy, not part of our solar system at all. Here's an artist's rendering based on the latest astronomical data about what our galaxy, the Milky Way galaxy, looks like. And the white arrow toward the bottom of the screen shows you the location of our solar system in one of those spiral arms. Our galaxy has about 200 billion, that's with a B, 200 billion other stars, of which the sun is one. And NASA work currently suggests that most of the 200 billion other stars in our galaxy are likely to also have planets. So although 200 billion stars in our galaxy is a large number, keep in mind that the number of planets in our galaxy is probably even greater. The diameter of the Milky Way galaxy is shown there at the bottom of the screen, of being 105,000 light years. Traveling at the speed of light, it would take 105,000 years to go from one edge of our galaxy to the other. So it's a fairly large piece of real estate. And putting it in terms of miles, I have the approximate number of miles that we'd need to travel across the galaxy. And that's 620 billion miles. So it's, again, a large piece of real estate. Our nearest galactic neighbor, the nearest galaxy to ours, and keep in mind there are about 100 billion other galaxies estimated in the universe. And this is our galactic neighbor. And for the next couple of minutes, we're going to take a tour of this Andromeda Galaxy, which is 2.5 million light years away. And again, is a spiral galaxy like our Milky Way, a bit larger. You can see it's 130,000 light years across instead of 105,000 light years across like our Milky Way. But we're going to take a tour. It has around 500 billion stars in it, in orbit around a central black hole region shown in very bright because the cluster of stars in there is just very, very bright. So let's take a Hubble Space Telescope tour of our nearest galaxy to give you a sense of scale. Keeping in mind that each of the stars that you will see are light years apart. So here we're going to take a 3-minute tour of the Andromeda Galaxy. Every point that you are seeing there is a star. There are no planets to be seen because they're too small to see, but every point you see is a star. Wow, a lot of real estate there. And our galaxy looks very much like that. Imagine all of those stars having planets. Most of them probably do. How do planets form? Well, here is a small part of our Milky Way galaxy. Again, a Hubble Space Telescope image of a column of gas and dust. A magnificent image. It's called the Pillars of Creation. And you can see it's around 5 light years in height, shown on the screen here. It's about 30 trillion miles. And within this, you can think of these strands of gas and dust as being the nurseries where stars and planets are formed. And there are stars and planets forming in that region now. Here is a computer animated video showing 266,000 years in the formation of a solar system. Now, this is a numerical model, but it involved ginormous quantities of computing power to generate this. But the red circle that you see here in the frame is on the scale of on the outer edges of our solar system. You can see at the top left there, it says 82,500 AU, which means astronomical units, 82,500 times the Earth-Sun distance across this thing. But that's about the size of our entire solar system, as I'll explain shortly. And at the upper left corner, you'll see time in currently showing 0 years. So you're going to see that racing along until we eventually get to 206,000 years. What we're going to see then in this brief animation is we're going to see this cloud beginning to collapse and spin around, and stuff is starting to form. So imagine stars and planets forming in this collapsing, chaotic cloud of gas and dust. And the reason I'm showing you this is watch the chaos, watch all the flinging of stuff around. And that is in the context of, where did Oumuamua come from? It came from another place, but why did it escape? You'll get a sense of that now. You can see the time ticking rapidly past in the upper left corner as this cloud, and the colors are referring to the density of gas and dust in this cloud. And you can see it's distorting. And clusters of gas and dust are forming. And look at that rotation, just like our solar system rotates. All the planets orbit the sun. And look at the stuff, wow, there's a lot of stuff flying around. Imagine those being stars and planets being flung out of this cloud of gas and dust. So what you've seen is an animation involving an enormous amount of computing horsepower to show you what a collapsing cloud of gas and dust, similar to what you saw on the previous slide, might look like over the course of a bit more than 250,000 years. And we saw a lot of stuff escaping. Now, in the left corner of this image here, which is a frame that I captured from that animation, you can see that spinning knot of gas and dust right in here that I'm circling. That would be about the size of our solar system. Imagine our planets orbiting a star right about there. And yet there's a lot of other material, planets and other things that have been thrown out and are wandering through interstellar space during the formation of that. And what you're seeing here then is animation. The red is Oumuamua. It came from way outside our solar system, from another part of the galaxy. And the yellow track that you'll see again being repeated here is a comet, which also was interstellar and came in 2 years after Oumuamua. Notice that they are not in the plane of our solar system. Our plane of the solar system is shown in that disk of the different planets there. And they came from way outside and they were really moving along. You can see the speeds shown at the upper left of the corner there. And you can see that Oumuamua really took a hard turn when it came by the sun. And the comet, shown in yellow, did not get as deflected gravitationally as Oumuamua did, because the comet didn't get as close to the sun as Oumuamua did. Now here's another way of looking at it. We're looking here at the inner solar system, the sun in the center, of course, Mercury, Venus, Earth, shown in blue, and Mars's orbit, shown in red. And the path of Oumuamua in 2017 is shown in that gray hyperbola coming through the slide here. And the arrows show the direction and the month and day at different places in its orbit or in its path through the solar system. The astronomers did not see Oumuamua until it got to the left side of the screen. Notice the yellow arrow and the yellow point labeled 10-19. Notice that Oumuamua had already come through the solar system and was on its way out of the solar system before we noticed it. Because of that, there was, and it was moving right along, and it was, as you'll see, quite small. There were only a short time to view it, only a matter of a week or so for even the largest telescopes to collect data on what the heck Oumuamua was. But here is an artist's rendering, an early rendering of what it might look like. And you'll see very shortly, why would anyone come up with a shape looking so strange as this? Well, it was presumed to have a low reflectivity. The word albedo shown here in the upper left. Albedo simply means brightness. How much light did it reflect? Was it shiny or was it quite dark? Well, the initial suggestions was that it had a very dark color, did not reflect much light. It was also reddish in color. It was, as this artist rendering suggests, very elongated. It wasn't spherical, it wasn't some random chunk. It was kind of pancake-like, and it was also considered to be poor in volatiles. You'll see how, as data were collected, you will see toward the end of our talk here in the next few minutes, how these various ideas withstood additional data. Here's a video from NASA describing its discovery at the Hawaiian observatory known as Pan-STARRS 1.
It was a special day when this object was first discovered. We have been waiting for the discovery of an interstellar object for decades, basically.
Well, when I first heard about this interstellar object, it was very exciting just from a scientific point of view that finally there's been an actual observation of such an object.
This object is simply a piece of another solar system that was expelled, and it has been traveling through interstellar space for hundreds of millions of years, billions of years, we don't know.
Number of our survey projects and other observatories immediately turned their telescopes to take observations of this object. From the observations we have so far, it looks like it's a very elongated object, maybe about a quarter mile in length.
We think this object, 2017 U1, is very long, perhaps 400 meters or so long and very narrow, skinny, perhaps maybe 40 meters or so in the other dimensions. That's a very unusual shape. We don't see that in our solar system. None of the asteroids in our solar system look like that. So it's very puzzling how it could have obtained this shape.
We also see that it's very reddish in color, which indicates that it's been possibly in space a long time and irradiated by not only the light from our sun, but other suns as well.
There's still quite a bit to learn about this interstellar object and limited time because it's on its way out of the solar system.
It's fading very fast. It's a relatively small object, so it's very dim. But we are continuing to try to use NASA assets like the Hubble Space Telescope and Spitzer to take observations to determine more about its size and composition.
NASA's Planetary Defense Coordination Office has a near-Earth object observations program, which funds efforts that survey the skies to look for near-Earth asteroids and to calculate their orbits and their trajectories and to determine if any of them might pose a hazard to Earth. And as part of doing that, some amazing discoveries can happen, and the discovery of this interstellar object was one of them.
As our observational capabilities improve, PanSTARRS has been getting better, other surveys have been getting better. There are a new generation surveys that will come online. We will be detecting more of these in the future.
Indeed. Stay tuned. There's a ginormous telescope which will be inaugurated next year to do exactly this work. So we'll be hearing more about additional interstellar objects ripping through our solar system regularly. What we're showing here is a logarithmic scale of our solar system. The sun is shown on the far left here. Our host of planets, the 8 planets, are shown here. And the numbers that you see, 1, 10, 100, 1,000, and so forth, are in terms of what are known as astronomical units. So, for example, Earth is 1 astronomical unit from the sun by definition. Saturn is around 10 astronomical units from the sun. But notice that the numbers go up by a factor of 10. So this is not a linear scale. This is logarithmic. What I'd like to show you then is this Oort cloud, the OORT cloud shown at the left here, which is the home of most of our comets. There are trillions of comets associated with our solar system, and they're way out there. Notice 10,000 to 100,000 times further from the sun than Earth is. And they're so far out, notice 1.6 light years, that they're getting out close to other stars. Well, the point of that is the following. It's a very important point to grasp, is that as stars are moving through the galaxy, as our star gets within a couple of light years of another star, gravity from that other star can fling comets from our system toward our sun, or alternatively, comets from their system can be thrown into our solar system. So you can exchange stuff between star systems from the Oort cloud, not only from our system, but Oort clouds that exist in other star systems. So it's a way of exchanging matter between star systems. For that reason, it was thought by astronomers that when we eventually saw an interstellar object in our solar system, it would be a comet. I'll repeat that. The expectations were that the first object, or most objects, that we would find coming through our solar system would be comets stolen from other solar systems that were coming into our solar system. Comets. Here's a comet seen by the European Space Agency Rosetta spacecraft. Here's a comet. It's around 2 miles across, the long dimension there. It's a chunk of, it's been described as a dirty snowball, a lot of ices and dust. And you can see jet going up toward the upper left there. That's a gas, a jet of gas and dust being ejected as it's being heated by the sun. It's blasting gases as the ice forms a gas and blasts dust away. That's what makes comets, what makes their tails. Well, here we go. Here's Oumuamua. It was not a comet. Here's Oumuamua on the left side of the screen. You can see that frame with the yellow arrow and the faint dot right in the center of that left frame. That's Oumuamua. It does not have a tail, but wasn't it expected that interstellar objects would be comets? Yes, it was expected that interstellar objects would be comets. Well, if they're comets, they should have tails of gases and dusts. Oumuamua didn't. That was its first strange thing about Oumuamua, is that it did not appear to be a comet. Well, 2 years later, we had another interstellar object rip through our solar system known as 2I Borisov, and by golly, it was a comet. It was a comet. So the second object coming from interstellar space was a comet, an interesting object. But curiously, the first object that we saw was not. In addition, another strange aspect of Oumuamua was that it was shaped in a very peculiar way. It was shaped, as you heard in that previous video, it was elongated. There are no asteroids in our solar system, none. We know of thousands of asteroids that have been measured. None of them have the shape of Oumuamua. So as you might say, what can an astronomer learn from that dweeby little point of light that you saw in that previous frame? It's just a point of light. What could possibly be gained from watching it? Well, its brightness changed over time. So what you see here along the x-axis here, the horizontal axis, is time, and the y-axis is brightness. Notice that it is changing its brightness. You can see those curves. Notice the data here, the different color points, that Oumuamua was changing its brightness. So it'll get bright, and then it'll get dim, and it get bright and get dim. And it was doing so with a period of 7.34 hours. So it was tumbling. It was tumbling, but it also had a change in its brightness of more than a factor of 10. So it was not a sphere. It was highly elongated in a shape that had never been seen before among any asteroids. So it was described in the video that you just saw, it was an asteroid. Well, yes, it appeared to be an asteroid because it did not seem to have a tail of gas and dust, but it did not have a shape like any asteroid that we had ever seen among the thousands of asteroids that have been measured in our solar system. So its shape was peculiar. The amount of the right-hand graph here shows you how much variation in brightness occurs among asteroids observed in our solar system. And the axis here shows that Oumuamua, notice it had a variation of 2, which is off the screen to the right, it had a variation in brightness greater than any asteroid that had ever been seen in our solar system. And this graph simply shows you the color of it. It had a lot of red in the upper left, and notice the large black point in the lower left here. So the right side of the screen is how bright in the red color was it? That's the large point on the right. And then how bright was it in blue? And that's the point at the lower left here. Notice that it was much brighter in red than it was in blue. How big was it? How big was it? Well, it depends on your assumption about what its reflectivity was. And the blue line here, that curved blue line, shows you it can almost be any size you want it to be, depending upon what brightness you make it. If it was a very bright object, it might be around 30 meters or roughly 100 feet across. If it was a very dark object, then it would be 150 meters or about 400 feet across. It all depends on how bright you think it was. We have no way of measuring its brightness. So that point of light, we don't have any, you'll see, knowledge of exactly what its brightness was. Was it a large dark object, or was it a small, bright object? And this is a really important graph. So hold on, grab onto something. This is really an important graph. This is showing you the acceleration as comets zoom past the sun, the gases and dust being expelled from those comets are like jets, like rockets, and they accelerate the comet away from the sun. Well, you can see there are the horizontal axis is showing you how much acceleration comets show. And you can see that Oumuamua, the black vertical line there, is on the right side of the screen. That's showing us that Oumuamua was really being rocketed away much faster than most other comets. Now, the take-home message here should be causing you to scratch your heads. And that is, if the acceleration is caused by the jetting of gases and dusts away from the object to propel it away from the sun, but Oumuamua did not show any gas or dust coming off of it. What was causing it to be accelerating so quickly? So the question was, and this is where the two hypotheses you're going to see right now came from. Was Oumuamua being pushed? Was it being pushed by the sun's light pressure, or was it being propelled like a jet expelling gases and dust, which we didn't see? So was it being pushed by the pressure of sunlight, or was it being propelled by the ejection of gases and dust like a comet? The first hypothesis you'll see now comes from Harvard University, former chair of the astronomy department at Harvard, and just a very famous, very impressive scientist, suggested that it was being pushed. It was being pushed. It was not a comet. It was being pushed by starlight. So in summary first, what did Oumuamua have? It had a strange shape. It was red in color. which means that it had been in interstellar space for hundreds of millions, possibly billions of years. Things just get red over time when they're exposed to cosmic radiation. It had no cometary tail. It had virtually no dust was detected. It had this strange orbit that had it coming in from interstellar space. It was rotating. It had this very high acceleration, non-gravitational acceleration. Its size was still unclear, and its reflectivity, again, albedo, was not directly measured. Theoretical models were the following, is that comets should be 200 to 10,000 times more common than asteroids. That interstellar objects entering our solar system should be overwhelmingly comets in nature, but Oumuamua appeared not to be a comet because it did not have the gas and dust. So here we go, hypothesis one, coming from Harvard University. Holy mackerel, look at this. Oumuamua is an ancient spacecraft. The reason it didn't have gas and dust coming off of it was because, of course, it was not a comet. Neither was it an asteroid. We don't have any shapes like asteroids. It was a spacecraft. It was a spacecraft from a dead civilization. Can you imagine what kind of reaction that got in the press and in the scientific literature? Holy mackerel, the first interstellar object we've seen in our solar system is a piece of space junk. Wow. They suggested that it is a light sail, something like this. The publications that Abraham Loeb and his co-workers did were beautifully numerical, beautifully thought out, and they concluded and have steadfastly stayed with the notion that this was a light sail from another civilization that came through our solar system. Oumuamua is a light sail. Some excerpts from Bailey and Loeb in 2018 in the Astrophysical Journal Letters. Here are a couple of excerpts. They conclude that it had a mass to area ratio of suggesting that it was made of material that weighed only 1/10 of a gram for every square centimeter. So a square centimeter is about 1/2 inch square. So if you had a 1/2 inch of something with a square centimeter in size, that would weigh about 1/10 of a gram. And that would require the object to be a thin sheet. So here's my prop. It would require it to be a shiny object. It would require it to be a shiny object with a thickness similar to what you see on the screen right now that I'm holding up. That's what their calculations indicated, that it would be shiny. It's a light sail, and it would be about the thickness that you see there. You're seeing it edge on. It would be made of aluminum or beryllium, an equation that they used for it to come up with that number. And here are a range of materials that it could have been made of. And I thought, wonder where they came up with 0.3 of a millimeter to 0.9 of a millimeter. They don't explain it. It's one aspect of the article that you really had to linger to find out what where they were getting these numbers. But the kind of materials that it could have been made of were aluminum, which is shiny, of course, or beryllium. Could have been like this. Or it could have been a mylar as well. Considering an artificial origin, they continued, one possibility is Oumuamua is a light sail floating in interstellar space as debris from advanced technological equipment. The light sail technology might be abundantly used for transportation of cargo by another civilization between planets or between stars. This would account for various anomalies of Oumuamua, such as the unusual geometry based on the light curve that you saw. Its low thermal emission suggested it was highly reflective. I didn't get into that, but NASA's Spitzer Space Telescope measured the infrared signal of Oumuamua and saw nothing. It was nothing. It was so small and so cold that it did not show up in infrared. It appeared to be not dark colored at all. It appeared to be shiny. That's how Bialy and Loeb interpreted it. I think they're right. Its deviation from a Keplerian orbit, meaning it was accelerating. Irrespective of the object's composition as it travels through the interstellar medium, it would have become red, and that is expected. Everyone agrees that an interstellar object will most likely be red in color, and it was. A survey of light sails as, here's an interesting word, Techno Signatures. Techno Signatures. A survey for light sails as Techno Signatures in the solar system is warranted, irrespective of whether Oumuamua is one of them. This gets to the idea of space archaeology that Abraham Loeb is discussing, the search for techno signatures. Their calculations suggested that the light sail was as thin as you saw here in my prop that I'm holding up. It was shiny. It was as thin as you see here. And it was probably about 92 feet across on a side. And that would have explained the data that had been collected, a light sail. So here is a brief segment from Professor Loeb.
There are more planets like the Earth in the observable volume of the universe than there are grains of sand on all beaches on Earth. What else is out there? Where is everybody? Why haven't we seen them? Well, if they're out there, the most natural answer to this question is that most of them are dead by now. We know from our own experience that developing the advanced technologies we have brings in the risk of self-destruction. But that doesn't mean that you cannot find evidence for them because they left burnt up surfaces or polluted atmospheres. So one can do space archaeology. And my hope is that this will be an important history lesson for us. By finding dead civilizations that didn't behave properly, they were not kind to each other or to their planet, we will learn an important lesson to do better and avoid a similar fate.
Professor Loeb has a best-selling book based on this hypothesis that you see here. The cover of the book is shown here. Very popular book. Hypothesis 2, the second hypothesis, which is only a few weeks old. It has appeared in the geophysical research literature. And it is suggesting something quite different. Again, using the same data as Loeb had used, their hypothesis is fundamentally different. And their view is that it is a nitrogen iceberg. A nitrogen iceberg. We've probably all seen liquid nitrogen, but if you cool it even further, nitrogen gas can, as you drop the temperature, nitrogen gas becomes liquid nitrogen, can eventually become nitrogen ice. And their suggestion is that it was not being pushed by the sun. In fact, Oumuamua was accelerating away from the sun, not because it was being pushed by sunlight, but was being propelled by escaping gas. Remember that no gas or dust had been seen, but their suggestion is that it was in fact being accelerated by the escape of gas. Quickly then, their excerpts from Jackson and Desch. I look forward to showing you the video of Jackson and Desch in just a minute, because it's really priceless. An excerpt from their recent papers. It has not been clear what ice composition could provide sufficient force to explain the non-gravitational acceleration while simultaneously remaining undetectable. Nitrogen in 2 does not have strong spectral lines in the infrared, making it hard to detect. Nitrogen outgassing would likely be best observed in the ultraviolet. Ultraviolet was not measured in the time frame that Oumuamua was ripping through our solar system. Ultraviolet measurements were not made. Infrared measurements were made, but nitrogen was not detected, but that's because nitrogen doesn't show up well in infrared. We infer the dimensions of Oumuamua to be about, and that's about 100, it's about 130 feet by 130 feet by about 30 feet. So very small object. This is the kicker. We conclude that Oumuamua is an example of an uncommon, but certainly not exotic object. It's a fragment of a differentiated Pluto-like planet from another star system. Where did this nitrogen ice come from? Their hypothesis is it was chipped off of a Pluto-like planet. Their calculations are dead on. It is just uncanny. It is dead on. I won't show you this graph any further unless you'd like to go back to it, but it is holy mackerel. This graph is just a holy mackerel moment. And you'll see the smile on Alan Jackson's face because when he's describing this agreement, the calculated acceleration for Oumuamua being propelled by nitrogen gas is the red line. That's the predicted, and the dashed line is the observed. Notice that the red line and the dashed line really agree very well. This is wow. It suggests that Oumuamua came into the solar system being quite large. In this upper right corner here, the upper right graph shows that as it was approaching the sun, it got hotter and hotter and its mass diminished dramatically so that by the time it was moving away from the sun, notice that graph showing this great drop in the curve here. It lost 92% of its mass as it went past the sun, and as it lost all of that mass, its shape changed dramatically. It was almost spherical when it was coming into the solar system, and then as it lost a lot of mass, it became pancake shaped. 2-to-1 going to 8-to-1. Why did they suggest a Pluto-like object? So here's Earth for scale, the moon for scale, and here's Pluto for scale. Notice that Pluto then is smaller than the moon. And NASA sent a spacecraft past Pluto a few years ago. It's still operating nicely as it goes toward interstellar space. Cross-section of Pluto looks something like this: rock on the inside, water ice above that in this cross-section, and then a large layer of nitrogen ice on the outside of Pluto. And here is an image taken by the NASA spacecraft, New Horizons spacecraft, showing what Pluto looks like. This is Pluto. Hello, Pluto. The materials that you're seeing on Pluto here, none of it is rock. All of it is ice. And most of the ice that you're seeing here in this image of Pluto, this image here in the front here is Sputnik Planitia, nitrogen ice, nitrogen ice. So if a crater were to be formed on a Pluto-like object and blasted the stuff off of the surface of Pluto, it would be nitrogen ice. The graphic in the upper left corner here shows you why Pluto is no longer considered a planet. Some of you may disagree with Pluto having been demoted to a minor planet instead of a planet. But Pluto orbits in a strange, highly elliptical, out of the plane of the solar system. Pluto is shown in that red thing there. All of the other planets orbit in that horizontal plane that you see here. Pluto is a rogue. It's orbiting way out of the plane by 17 degrees. So here's an interview with Professors Desch and Jackson. And I would ask you to watch. These are scientists. They have to be very serious. Scientists have to be very, very serious. Keep that in mind, very serious. So Jackson here, he is trying to hold back his enthusiasm. Just watch his lips. He is trying to laugh, but he knows it's not appropriate that he should laugh. He's trying to hold back a smile on several occasions. He is so great, I can't stand it. So anyway, here we go.
Well, any astronomer was very interested in this object, including me, because this was the first time we had confirmed that an object was coming in from outside of our own solar system. This is the first thing we ever saw that was not part of our solar system.
There were a few things about Oumuamua that were, the specific object, that were unexpected and unusual. So initially people thought that it was this very long, like cigar-shaped object. So when we saw it, people initially thought that it was an asteroid because it didn't have a tail. It was just a point of light. Comets have these big, beautiful tails because they are evaporating lots of gases like water and carbon dioxide.
If we could figure out what unusual circumstances or what circumstances at the beginning of our solar system might have created an object just like Oumuamua and give it a natural explanation.
When we had more observations, we found that there was this small rocket effect like you get for a comet, which was then, okay, how do you match the fact that it has this comet-like rocket effect, but you didn't see the comet tail?
And we settled on the composition of nitrogen ice, frozen ice. And this was very attractive from the very beginning because this is an ice that we do see in our own solar system on the surface of Pluto. So it was, we reasoned it was possible that there could have been Plutos and other solar systems with nitrogen ice on their surfaces, and a piece of it knocked off could have entered our solar system and explained everything we saw.
And so then we went through the calculations, and the reflectiveness that you need to exactly reproduce the rocket effect that we observed is the reflectiveness of the surface of Pluto, which has a lot of nitrogen ice on the surface. So that was like, we hadn't necessarily been expecting that, and it just fell out, and I was like, okay, that's amazing. That's great.
Hold back that smile.
It fits everything we know about it. It seems reasonable to conclude it as a piece of another planet. And it's a planet like Pluto. That's exciting to have a piece like that in our own backyard. And more than that, it tells us that the things that happened in our own solar system, where you had Pluto's forming and banging into other icy objects and fragments flying off, all of these things, we learned that that probably did happen in our solar system as a result of this research. And it tells us this is probably a near universal process and that other solar systems are doing the same thing that our solar system did.
In the process of doing that, just like if you have a bar of soap and you're using it in the shower, once you've been using it for a long time,
you might start off with a fairly chunky bar, but you end up with this annoying little sliver. And exactly the same kind of thing happens, that if you're just removing layers of material off the surface, then it slowly makes that flattening more extreme. And so that very naturally also explains why it was so flat when we observed it. It wasn't that flat when it came into the solar system. It's just that during the course of going through the solar system, it lost something like 95% of its mass because it went closer to the sun than Mercury. And that evaporated so much material that we were just left with the little soap sliver by the time we actually saw it.
So the current scientific consensus, you've seen two hypotheses. One, which has been highly publicized, the idea that it was a piece of ancient technology from another civilization. And the newest hypothesis that is only a few weeks old, suggesting that no, it's actually a natural object, but from a strange circumstance, that is a ice from a Pluto-like object in another solar system. Here is the current scientific consensus on Oumuamua. Understanding, of course, that science is not a democracy. Scientific consensus is a consensus, and of course, consensus can be wrong, but the consensus currently is that the solar sail hypothesis by Loeb and his co-workers is not a good idea, according to most astronomers. In order for a solar sail to cause the observed acceleration, it needs to remain properly oriented towards the sun. Just as you sail in a sailboat, you have to have the sail in the right orientation to the wind to be propelled along. So too for a solar light sail. But we saw that Oumuamua was tumbling, and therefore the solar sail, if that's what it was tumbling, so the acceleration would have been diminished. The consensus concludes also, while Oumuamua presents a number of compelling questions, we have seen that each can be answered by assuming Oumuamua to be a natural object, not something from another technological society. Assertions that Oumuamua may be artificial are not justified according to this group when the wide body of current knowledge about solar system minor bodies, asteroids, and comets, and planetary formation is considered. So that is the scientific consensus as it occurs now. I end then with just a couple of more slides, and that is the Copernican and cosmological principle. Habitable planets like Earth are likely to be representative of the norm and are therefore not special. It's an interesting concept, and as the number of known planets, measured planets in our galaxy is approaching currently 6,000 and growing, we should keep this Copernican or cosmological principle in mind. Carl Sagan once said, extraordinary claims require extraordinary evidence. This phrase is a paraphrase of what Laplace said several hundred years ago. The weight of evidence for an extraordinary claim must be proportioned to its strangeness. This is one of the principal criticisms of the Loeb hypothesis, is that they needed extraordinary evidence to make an extraordinary claim of a technological origin for Oumuamua. And probably many of you, all of you perhaps, are familiar with Occam's razor. Entities should not be multiplied without necessity. The simplest explanation is usually the best one. Excuse me. In summary, We started with this slide. It was originally suggested that Oumuamua was a dark object, low albedo, a dark object, reddish, elongated, and volatile poor. It is now suggested that both of those things are wrong. That in fact, it was a bright object, just a small one, with a high albedo, a high reflectivity. It was icy. And it was volatile rich. The volatile was not water ice or carbon monoxide ice. It was nitrogen ice, and it also had negligible dust. In summary then, keep this telescope in mind. Look at the size of this mirror. This mirror here is over 27 feet across. And it is the mirror that has been installed in a new observatory being built in Chile, and it will become operational next year. It's a very large telescope, and its purpose is to scan the skies, looking in part for interstellar objects coming into our solar system. It is expected that the Vera C. Rubin telescope, previously known as the LSST, will be discovering interstellar objects at the rate of 1 per year, beginning somewhere around 2022. In conclusion then, we've seen Oumuamua was the first interstellar object that came into our solar system that we actually observed. Initial ideas about it were flawed because they were based on flawed assumptions. For example, it was large and it was dark colored. No, it appears to have been small and bright. It appeared initially to have no gas coming off of it. In fact, now it appears that it had lots of gas coming off of it. It was just gas that could not be detected at the time. So as interesting and as fascinating as the Loeb hypothesis was, that it was an interstellar object from a dead technological civilization, it appears more likely that it is a natural object, a very interesting, unusual object from interstellar space. Thanks very much.
Thank you, John. Very interesting. Dave, do you have a question?
Hi, Dave.
Hi, John. How you doing? Fascinating story. I really loved it. I guess I have a bunch of questions, but let me ask just a couple to start with. One, I would have thought that there would have been a lot of stuff out there in interstellar space, and that if there was a lot of it out there, and the solar system is a pretty big thing, that this stuff would have been going through the solar system on a pretty regular basis. Now, is that my intuition completely off base, or is it just that we're not looking in the right way, or have we never seen one of these before?
It's not off base. It is not off base. It's the matter of, can you get good enough instruments to be able to see the really small objects coming through? It is suggested, again, model dependent. We don't have a lot of data, but it is suggested that there are objects going through the solar system right now, perhaps upwards of a dozen of them, but they're too small to be seen with current telescopes. So that's why that very large mirror that you saw in that one of the last slides is a very large mirror, which will have a very large field of view for being able to scan the entire sky every night. Every night, it will get a scan of the sky from Chile, and it will be able to see those objects that you and most other astronomers are expecting to see. So yes, you're correct. The number that has been suggested that when solar systems like ours form, the number of objects being flung around, remember that early video showing that red cloud collapsing and stuff being thrown out? The number of objects being thrown out of our solar system early on was somewhere in the number of 1,000,000 billion pieces of junk being thrown out of our solar system into interstellar space. So there's a lot of stuff out there. And whenever you watch Star Trek and they say, go to warp 6, I hope they have a good map. Otherwise,
right.
otherwise you end up with a lot of stuff, have a lot of bugs on the windscreen there, you know?
Hi.
Hi.
So unfortunately, I missed part of the talk, so forgive me if you talked about this, but do we have an idea how long Oumuamua has been traveling? Since we know, and do we know actually more about its origin and its longevity, how long it's been traveling?
A very good question, of course. Astronomers have calculated backwards in time to find out where in the galaxy it could have come from and whether that path going backwards in time may have come close to any stars that we currently see. The answer is the following: no unique solutions. It is the red color that you see indicates that it has been traveling through interstellar space for minimum, the guesstimate is minimum of 500 million years, and possibly longer. Things become redder the longer they're in interstellar space because they end up collecting organic junk that is floating around as molecules in interstellar space. And as that organic stuff is irradiated with cosmic radiation, it becomes reddish. So that red color is the best current estimate of the time of travel. Half a billion years is a good number. The closest star that it comes to is the star Vega that we can all see in the northern sky, Vega. Vega is 27 light years away. And interestingly, probably just a coincidence, but interestingly, the Vega system formed, guess how long ago? About half a billion years ago. Now, it's most likely a coincidence, but Oumuamua was thrown out by another planetary system, at least a half a billion years ago.
Dave has a question here about how about intergalactic objects?
Intergalactic objects. I'm pausing because as you know, the space between galaxies is really huge. The likelihood, it seems, and this is only intuitive, I've never read any paper from any astronomer who has suggested debris from another galaxy. I think because the probability of capturing objects that have traveled through 2.5 million light years or more of space is as close to infinitesimally small as we can imagine. The nearest star to us, of course, is only 4 light years away. 2.5 million light years compared to 4 light years is really quite large. So the probability has to be much lower.
So we need them to put another wormhole up there, right?
That's right. Yeah, that's right. The Deep Space Nine, we'll have to contact Deep Space Nine to find out about wormholes. For those of you who don't know about Deep Space Nine, that was a Star Trek episode as well, or a Star Trek series. My apologies for anyone who knows that series. So keep in mind, while there's a lull in the action here just for a moment, keep in mind that Oumuamua was merely a point of light. You saw the image. It was merely a point of light, and yet that point of light contains really quite a lot of information about it tumbling, its shape, and its composition, and a variety of other things. So it's amazing what physicists and astronomers can come up with such a small amount of information.
Could you just say a few words about this heliosphere? I've not heard that concept before.
Yeah, the heliosphere is considered to be the boundary between boundary in space. And Voyager 1 and 2 spacecraft that we launched over 40 years ago, the United States has done some remarkable stuff that no other nation has even attempted. We're launching interstellar objects. We have launched interstellar objects. So it has found the helio boundary, and that is, here's the sun. So here's my prop, here's the sun. And it's sending out cosmic radiation. And Voyager left Earth and has been traveling away from Earth for more than 40 years. And it is measuring how much cosmic radiation coming in from the rest of the galaxy there is compared to how much energy is coming out of the sun. And that boundary, known as the heliopause, is the point at which the pressure of cosmic radiation coming into the solar system is equal to the pressure of stuff going out of the solar system. So it's a boundary, and that boundary is the heliosphere, interstellar space. And Voyager 1, the United States has gone into interstellar space. And that's why Carl Sagan wanted to put a record and image on the Voyager spacecraft, so that if those Voyager spacecraft are ever found by another civilization millions of years from now, they will know who sent it, when we sent it, and where it came from. And those were, that information is contained on the plaque that is on the Voyager 1 and 2 spacecraft. So Carl Sagan, again, was ahead of his time with this idea of space archaeology. And we, the United States, has contributed to interstellar space archaeology. So when this telescope becomes operational in 2022, the Vera C. Rubin telescope becomes operational, we'll see whether there are other objects out there that might ultimately prove to be pieces of another culture. Wouldn't that be a kick? I think it would make it. I think it would be in all the newspapers.
This question from Greg. If much of the objects sublimated near the sun, wouldn't the surface be relatively fresh? For example, uncontaminated with organic material from space?
That's a very good point, Greg, and that's something that was not addressed. I wondered much the same thing. That was not addressed in the 2 articles by Desch and Jackson. Interestingly also, when Professor Loeb and his colleagues wrote a rebuttal to the Desch and Jackson hypothesis, they did not raise that point. So I think your point is well taken, that the reddish color remains curious if so much of the mass had been sublimated off as it passed close to the sun. I think there's probably a way around it by suggesting that even the nitrogen ice, even after you blasted away most of the nitrogen ice down to fresh nitrogen ice, there was still organics in that nitrogen ice, which may have given it the reddish color. But your question's a very good one, and I think is the weakest aspect of the Jackson hypothesis. Very good.
So we got a question from Bruce saying, what would be better, money notwithstanding, Earth-based telescopes or space-based telescopes?
Both are going to happen. Both are going to happen because both have their advantages. For example, there is a current study, a feasibility study going on in NASA now. No money has gone to building it. Small amount of money is going to explore the possibility of building an automated radio telescope on the far side of the moon in a crater. So you land a couple of robots at a particular crater on the far side of the moon, and then you have these rovers chugging along, dragging a net, a metallic net behind them as they use the crater to form a dish. We've seen parabolic dishes for televisions and so forth. You can have parabolic dishes for radio telescopes. And the far side of the moon is great to do that because you're away from the radio noise coming from Earth. And the importance of that is if you wanted to detect a civilization out there somewhere in the galaxy that is broadcasting radio signals, you want to get away from this noise from Earth-based stuff. And by being on the far side of the moon, you're shaded from that. And you would, anyway, just be, holy wow, would that be great or what? The space-based telescope known as James Webb is scheduled to be launched next year. This is, if it's successfully launched, it was just delayed again a week ago. But if it is successfully launched, it is going to be a game changer. It's an astonishing piece of equipment. And it's just as Hubble has revolutionized our view of the universe over the 30 years that it's been, the James Webb Space Telescope is going to just blow our hair back. And then we have ginormous Earth-based telescopes, some with mirrors over 100 feet across, that are currently being built in South America on the top of the mountains there. And those are, the biggest one is being built by the European consortium. And it's going to happen in the next year or so as well. No, a little more than a couple of years. But it's going to be, so the answer to your question is, let's do it all. Let's do it all. Again, the money is comparatively trivial. Trivial compared to expenses in other things such as defense. It's trivial.
I just wanted to let the professor know, I'm sure my name is not connected with the Arecibo radio telescope in any kind of public way, but I was the chief surveyor back in the mid-70s that did the final calibration, the surveying for the final calibration of the Arecibo radio telescope.
Outstanding, outstanding. Yeah. What a legacy. What a legacy that instrument had.
Yeah. We tried to get it within 3.5 centimeters RMS, millimeters RMS, 3.5 millimeters RMS. We were able to get it down to about 5 millimeters, half a centimeter RMS. And believe it or not, they were not happy that we didn't achieve the contract's specifications. But later on, using much better equipment, which we didn't have available, they were able to meet that 3.5 millimeter specification.
Outstanding. Congratulations. What a great achievement.
Great. We have a question in the chat box from Lucinda. She says, bodies like Sedna, which is an inner Oort cloud object, are also red. Why could not Oumuamua be an Oort cloud object deflected into the heart of our solar system by a passing star, as Schultz star passed through only 70,000 years ago?
Yes, that has been examined indeed. That could have been that has been suggested. It is not considered likely, although the process that you mentioned is possible. It's just not likely that it applies to Oumuamua. You're right. Those objects are red like Oumuamua, correct? But Oumuamua is not considered to have come from deflection from the Oort cloud. Interestingly, it is thought that some of our long period comets in our solar system could be captured other objects from other solar systems. So doing a process similar to what you just suggested, it's being suggested that Techno Signatures, again, Loeb's concept, if there are objects from another solar system, I mean artificial objects out there, they could be in the Oort cloud. Because as we drift by, we captured some of their technological debris long ago. So this Vera C. Rubin telescope will be surveying lots of possibilities. There could be, we may have collected a lot of junk in the last 4.5 billion years of our solar system, and some of it may be from prior civilizations. That has to make you smile. Wouldn't that be great?
Al, do you have a question?
I just wanted to say that fantastic presentation, but no little green men tonight.
No, thank you, Al. Not yet, but that
Not
just
yet.
means that not yet.
I know you're on the trail, though. You're on the trail.
We almost we think we've seen a broken branch. We haven't seen the footprints yet. So
I love your enthusiasm.
thanks. You know, we can't predict when that might happen, but the search is on, and the instruments that are being built in part to do it.
Oh.
So the longer it takes, the more exciting when it finally happens, the more exciting it will be when it happens.
And I guess with that, we will end. So thank you, John. Yes, I have to agree. I love your enthusiasm, and you make these talks so interesting.
Thank you very much.
Yes. So thank you all for joining us, and have a good evening. I look forward to seeing you at the next lecture.
Thanks again, everybody.